In this video, we'll learn about Irradiance Point Cloud GI engine. First, we explore how it works and then take a look at its parameters, and after that, we'll be trying to utilize it in our scenes. Let's open up our render settings and go to the Global Illumination tab. You notice Irradiance Point Cloud is only available as a secondary GI engine. The reason being is that it's not quite good at picking up details, and that's why it is more suitable to be used as the secondary GI engine. It's on purpose so we can get our secondary bounces quick. So in most cases, you use brute force as your primary engine and Irradiance Point Cloud as your secondary GI engine. As we learned, you can use brute force as the secondary GI engine as well. Let's open up Redshift Render View and see how Irradiance Point Cloud works, which is a bit different compared to the overall way that brute force or Irradiance cache work. And load the render from our side view. Also, we can have our render settings window open as well. Our camera is roughly here. First, some rays are sent out from the camera into the scene. Whenever these rays hit a point on the surface, they create an Irradiance Point Cloud sample, and each ray will continue to bounce in the scene and create samples until the bounces value limit is reached. In this case, the bounces value is set to 4. 1 is for the primary engine and the other 3 is for the secondary engine. So each secondary GI engine ray can bounce 3 times, and whenever they hit, they create a sample. Each of these rays that come and bounce in the scene store all of that information in their path. And as we'll learn earlier in this section, these rays carry information between surfaces, and this is how Point Cloud can give us our global illumination solution. If you remember, in previous videos, we talked about the primary and secondary GI engines and how primary GI engine is responsible for the first bounce and the secondary GI engine is responsible for the subsequent bounces. It doesn't have to happen sequentially. So if we are using brute force as our primary GI engine and Point Cloud as our secondary GI engine, it's not like the primary GI engine first sends out its hemispherical burst of red rays, then when they hit a point on a surface, the secondary engine takes over for the next bounces. In fact, what happens is that when we use Point Cloud as our secondary GI engine and start the render, first Point Cloud, like I showed you here, starts sending out its blue rays from the camera and bouncing them in the scene back and forth and create its samples. Then when the primary engine sends out its red rays from each of its samples to collect information from the scene and get a proper calculation for that sample, the Point Cloud samples and bounces are already there in the scene. So the red rays can simply use the information that is stored on those secondary GI samples and bounces. Those blue samples and arrows, I mean. Obviously, I'm using these colors to make it easier to understand, and there are no such things as blue or red rays. Now, it can be a bit confusing, but you really don't need to know all of these details. You just need to know how to utilize these engines in your projects. Let me change the layout to this RS01. When Light Cache is used as our secondary GI engine and you start a final render, you notice before the final render begins, Redshift first computes the Irradiance Point Cloud, which takes a few moments, then the final render starts. If I just attempt another render, you can see that in the render view status bar as well, it says Irradiance Point Cloud for a brief moment before the final render starts. Now, Irradiance Point Cloud has a few parameters compared to brute force. Let's take a look at them and see what they do. As Point Cloud is a secondary GI engine, it's hard to demonstrate these parameters with examples, and I don't think we need to do that here. I'm just going to give you a brief explanation and then move on to other things. This samples per pixel controls the number of rays that are cast from the camera per pixel. Obviously, the higher the number, the higher the quality of your samples, and therefore the higher the quality of your renders. For scenes that have a lot of direct lighting, you can use values like 8 or 16, and for scenes that have a difficult lighting, i.e. direct lighting can't reach most of the surfaces, you need to use values like 32 or even higher, 64. Next, we have this screen radius, which is by default is set to 16 pixels. I'll be using Redshift docs to explain this parameter as I couldn't explain it better myself. We know Irradiance point cloud stores samples around the scene. It can't store a point for each ray that was shot from the camera because doing so would generate an extremely large number of points for high resolution images. Instead, it uses a screen space metric to space out these points, so the screen radius parameter refers to pixels. And this parameter affects two things. First, the used video card memory. Setting screen radius to larger values means that fewer points will be created and therefore less video card memory will be used. And also how often the results can be used by the primary GI engines. If the points are very far apart because of a large screen radius value, then the primary GI engine will not use those samples as often. So this can affect the performance of the primary GI engine. Therefore, lower screen radius values can translate into better rendering performance overall, or a better GI solution. Oftentimes, a setting of 8 or 16 will work fine. If your scene is of a high resolution, 2K or larger, you can try larger values such as 32 or 64. Another important parameter here is this retrace threshold. At the start of this lesson, I mentioned that Irradiance point cloud is not very good at picking up details. So the secondary GI samples created by the point cloud cannot be trusted in more detailed areas of the scene. So we are using the retrace threshold value to tell our primary GI engine to avoid using point cloud samples in corners and detailed areas to avoid artifacts, splotches, and light leaks. The larger the retrace threshold is, the more these points will not be used around corners and creases. Normally around 1 to 3 pixels would be enough in most cases. When rendering animation, you might need to use higher threshold values. Let me quickly show you how the threshold value can be useful. I'm gonna unhide this plane geometry and turn on this area light that is right behind it. If I set the retrace threshold value to 0 and render the scene, you notice we get these artifacts in form of light leaks down here. That's because right now those untrusty point cloud samples from this corner are being used in our final solution. If I increase it to 1 and render the scene again, the issue is less evident, but we still have some light leak left. Let's try 2 and render again. It's almost gone, but we still have a bit light leak left. Let's try 3 and render again. We can actually see the leaky samples in the point cloud calculation before the render starts, but during the final render, they will be ignored by the primary engine because we have used a higher retrace threshold value. And now at retrace threshold of 3, the light leak issue is completely gone. For now, let's set it to its default value of 1 and hide the plane and turn off the light. Now let's take a look at this point cloud mode up here. We have 4 modes: rebuild, don't save, rebuild, pre-pass only, rebuild, and load. Rebuild, don't save means that Redshift will compute a new Irradiance point cloud from scratch for each frame, but will not save it to disk, and the frame will be rendered after the point cloud computation is finished. So in this mode, when we start a final render, the Irradiance point cloud will be calculated but not saved, then the final render begins. Rebuild pre-pass only means Redshift will compute a new Irradiance point cloud from scratch for each frame and will save it to the user specified file down here. The final rendering pass will be skipped. So while in this mode, if I start a render, The point cloud will be calculated and saved on disk, but the final render won't start. You can change where you want to save that file right here. And when mode is set to rebuild, Redshift will compute a new Irradiance point cloud from scratch for each frame and will save it to the user specified file here. The frame will be rendered to completion as well after the computation of the Irradiance point cloud and saving it. So while in this mode, if we start a render, point cloud will be calculated and saved in this path here, then the final render starts. And when mode is set to load, we simply tell Redshift do not calculate point cloud from scratch before starting the final render. Just use the file that we have previously saved using rebuild or rebuild prepass only modes. So if I start the render right now, Redshift will start the final render immediately and uses the previously saved point cloud computation instead. We'll learn about these modes more when talking about global illumination consideration when rendering animations later on in this section. And finally, there is this frames to blend option here. It allows averaging the result of multiple Irradiance point cloud files, one for each frame together, in order to improve any flickering effects that might be present. That means if this value is bigger than 0 when rendering a frame in an animation, the point cloud calculation that are previously saved for adjacent frames will be blended together for a more accurate result. For example, if we are rendering frame number 5 in our animation and the frames to blend is set to 1, the point cloud files for 3 frames will be blended together. Frame number 5 itself, 1 frame before frame 5, and 1 frame after it. We'll learn how to use this value in practice when discussing global illumination considerations for rendering animation later on in this chapter of the course. For now, let's move on. Now let's see how we can use light cache in this scene to take a nice and smooth final render. The primary engine is brute force as always. Make sure secondary GI engine is Irradiance point cloud. Bounces is set to 4. Let's change the point cloud mode to rebuild, don't save. As it's a very simple scene lighting wise, the default value for screen radius, sample per pixel, and retrace threshold will be enough. Let's just go to the sampling tab and decrease our noise threshold to 0.004 and take a final render. And we get this nice clean render in only 11 seconds. Let's open up the second scene for this lesson, which is our complex interior shot, this classroom scene, to learn how to use Irradiance point cloud as a secondary GI engine in a more complex scene. I'm going to open up the render settings and go to the global illumination tab. Again, the primary engine will be brute force. The secondary engine will be Irradiance point cloud. As we are dealing with a more difficult lighting and direct lighting can't reach to a lot of surfaces in the scene, we can use lower screen radius like 8. Probably 16 would be enough, as we are just rendering a simple HD resolution render, and maybe a higher samples per pixel like 32. I'm also going to increase my retrace threshold to something like 2 to avoid any possible artifacts and light leaks in the corners. Finally, let's go to the sampling tab and make sure the threshold value is around 0.003 to clean up some of the high frequency noise. Now let's take a final render. And here is our final render, which only took around 45 seconds. One thing I should have mentioned earlier is when running IPR in the render view, as it is intended for real-time feedback, brute force will be used as the primary and secondary engine, even if you have point cloud defined as your secondary engine in the render settings. So that's about Irradiance point cloud as a secondary GI engine. See you in the next video.